Hello everyone, I'm Altaf Bukhari and today we are going to discuss vibration measurements and analysis. We will be covering the following topics in the upcoming slides. Now let's move on with our first slide. First of all, we have the measurement chain. As we discussed in our first video, the measurement chain, it is a basic chain for our desired output. First of all, we have a transducer that generates a signal. Then we have a preamplifier that amplifies the generated signal. Our signal can be of the lesser amplitude, which cannot be transmitted to our required destination. So we need preamplifiers to amplify our signals. Then we have filters to cut out all the extra vibrating elements, to filter it, to give it a proper smooth curve. Then we have detector or averager. Now this is a very useful component, uh, and we will discuss it in detail in the coming slides, so don't worry. Then we have our required output. Now let's discuss them in detail. Now, why do we make a frequency analysis? There is a sensor on the top of the gearbox, and it functions in a way, and all the curves, all the peaks in the amplitude frequency diagram show us a mass in the gearbox. Now, this gearbox is very important. It is a very useful application in mechanical vibrations. And a sensor is attached on the top, and then we get this amplitude time curve and the amplitude frequency curve. We can observe the the graphs in the time and frequency domain. Now let's move forward to the frequency analysis. As we discussed earlier, there's sensor, and then we have amplifier, then we have the 5 components that we discussed earlier. There's acceleration level and frequency, and it gives us a proper frequency curve of how our signal is, where is its peak value, where is its minimum value, and what needs to be trimmed. Now we have frequency spectrum or overall levels. In the frequency spectrum, in the first figure, we see the example of a fan. Now there's vibration and frequency. And there is one component whose frequency is relatively increasing with time. So it means that that part is damaged. It is giving more vibrations than required ones. So in order to overcome that, in order to keep our system functioning properly, we change that part. And we get this figure by using special sensors that we will discuss in details in the coming slides. And then in the next example, we have a gearbox in which we have an other component that is at level 1, which is lower at the bottom, and then then its frequency, its vibration is increasing with time. Its vibration is increasing. Sorry. Its vibrations. The vibration is increasing with time. So as the vibration is increasing, we know that this part is unbalanced. So we need to either remove it or we need to see how it can be balanced, how we can smooth out its frequency. Now, as it is relatively increasing, we know that this part is damaged. So we need to focus on this, and then we need to change it. Now, presenting the data, there are 3 basic types to present the data. There's the linear scaling, or there's logarithmic scaling. Then we have the amplitude in decibels. Then we have the linear and logarithmic frequency scales, that is decades or octaves. We will discuss them, don't worry. First of all, we have linear and logarithmic scales. First of all, we have linear and logarithmic scales. Now, in the linear scale, it shows that our tank is almost a quarter full, while in the logarithmic scale, it shows that our tank is half full. Now you see these two fluctuations, these two different values. So Why do we use them? Why do we use the logarithmic scale if it is so wrong? Now we will be explaining that in the coming slide. Why do we use it? Why is it so important that we have to consider it? First of all, there's linear versus logarithmic scale. Now, in the linear scale, we see that the distance between 0 and 0.1 is 1 decade, and from 0.1 to 1 is another decade. While in logarithmic scale, all the decades are of similar length. Now, due to these changes, due to these shifts, we see that variance that was shown here. In the linear scale, we could see a small portion, while in the logarithmic scale, it showed us that half the tank is full. Now, we have these two frequency scales, and let's see what is given to us by both these different scales. In the linear frequency scale, we can see the top curves and the bottom curves. It is well refined. The vibration levels and the frequency scales are well refined, and we can differentiate between all of them. While in the logarithmic scale, the lower portions are well refined, while the higher frequency is jumbled up. So, in order to see the lower frequency in the lower frequency where it is affecting our system, we need to use the logarithmic frequency scale. Now we have bandpass filters and bandwidth. Now, it is easier to observe it in the frequency diagram. First, there's a given bandwidth, and there are two different definitions. That is a real filter bandwidth and definition of 3 decibel bandwidth and the definition of noise bandwidth. Now, in the definition of 3 decibel bandwidth, in the figure in the lower left corner, we see that at the 3 decibel place, at the minus 3 decibel, we get a proper rectangle, and the area under the curve is our required area, while in the noise bandwidth we have this bigger rectangle that is shaded. We use this area under the curve. Now, these are two different frequencies, and two different definitions of the bandwidth are used. Now, why do we use them and how do we use them? Let's discuss it. Now, first we have filter types. We have filter types of constant bandwidth and filter types of constant percentage bandwidth or relative bandwidth. In the constant bandwidth, we focus on the bandwidth that is the frequency which is obtained in hertz. We focus on 3 to 16, and then b is equal to 10, and then b is equal to 31 to 6. Now, here we have a given bandwidth that is keeping constant, and from there we choose the area under the curve. But in the logarithmic frequency, we use percentage or the octave system. Here we see 3% or 1/3 octave or 1 octave. We use that area under that curve, the shaded region. Now, types of bandpass filters, the constant bandwidth filters, where the bandwidth is constant and independent of the center frequency of the filters. Constant percentage bandwidth filters, where the bandwidth is specified as a certain percentage of the center frequency, that is, the bandwidth is increasing for an increase in center frequency. The constant percentage bandwidth filters are sometimes called relative bandwidth filters. Now, in constant bandwidth filtering, the bandwidth is constant at 400 Hertz. We see its relations in linear frequency axis and in logarithmic frequency axis, where the bandwidth is being kept constant. Now, in the linear frequency axis, we have one bandwidth of 400 Hertz. Then, after a uniform distance, we have another peak of 400 Hertz, and then after another uniform distance, we have another peak of 400 Hertz. While if we look at the logarithmic axis, we see that it is gradually increasing, and then we get a maxima because the first figure, it is starting from 0 and then it is going towards 400 hertz. In order to reach that value in the logarithmic frequency axis, we see that the first figure has been stretched out, starting from 0 and relatively increasing to 400, while in the linear frequency axis, we just get a peak. Due to these detailed and refined figures, we have to use the logarithmic frequency axis. The importance of logarithmic frequency axis is being explained here. I'm not saying that you don't have to use the linear one. We have to use both. But since logarithmic axis showed a variation that almost a quarter of the tank was full, and it showed that half the tank is full, it showed a huge error. So now I'm trying to explain that why we reconsider that error and why we keep using this criteria. Now we have constant percentage bandwidth filters. Now we have 1 over 1 octave, that is 70% of the center frequency. Now first the constant bandwidth was given in hertz, but now it is given in octaves. And as we know that the logarithmic scale uses octave system. So in this figure, the linear frequency axis shows us a peak, and then it starts from 0 at 4K, and it keeps on increasing, and then it becomes constant. That is at 70%. But in the logarithmic frequency axis, we see those three peaks similar to the ones that we saw in the 400 Hertz diagram for the linear frequency axis. We now get them for the logarithmic frequency axis. Now we move on to the linear and logarithmic frequency scales, and it is a similar diagram where in the linear frequency axis the figure is well refined, all the peaks and all the bottoms, while in the logarithmic scale the bottom portion is well refined while the peaks are submerged. Now we have filter bandwidth, and we see them, the vibration levels, in two different ways. First one is with the area is different, and with this greater frequency that is starting from one point and going onwards and ending at another, due to this larger bandwidth, we get a sort of a bar graph. We don't have a refined value, but for a smaller filter width, we get a refined frequency and vibration level figure. Now, bandwidth and time, we have this rule that bandwidth multiplied by time should be greater than or equal to 0. Now this is also known as the uncertainty principle. Now we see the advantages of a logarithmic amplitude scale. The first one in the blue is the linear amplitude scale. It shows us the peak values, the exact values, and not the combined effect, while in the logarithmic amplitude graph, we see that the green portion of the graph starts before the linear amplitude and keeps on going. And especially the small regions, the small blue bars, the portions that come later on in the linear amplitude, they are shown vividly in the logarithmic amplitude scale. Now we move on to the decibel scale. Here we are shown some logarithmic amplitude figure of the decibel scale, how it varies from the acceleration in meter per second and the acceleration in decibels, and how the conversions happen. This is a simple figure with the required relation, and then we see the transmission of vibration. We have input forces, and then we have a system response, and as a resultant we get vibrations, as we discussed in our first video. we have forces, and then we have structural parameters. We have the vibration parameters. We discussed them all in detail in our previous video. Now we have a few examples in the two different scales, the decibel scale and the meter per second scale. In the decibel scale, the vibration level, the frequency in a building is 0 decibels or 0.000001 meter per second. And rocking a baby's cart can produce almost 60 decibels, which is equal to 0.01 meter per second. While a CNC machine, a lathe machine, or a washing machine produces 120 decibels. A CNC machine produces 120 decibels, which is equal to 1 meter per second. And then we have 180 decibels that equals to 1000 meter per second. And this, the worker drilling the pavement equals 240 decibels or 1 million meter per seconds. Now we have three different parameters that we discussed and how they affect us, how we get their relations. Here we see that the velocity curve seems quite settled, while the acceleration and displacement curves are in a curvature, are in a slope. Now, which parameters do we choose? In the first figure, we see that the displacement is quite linear, it is quite steady, while the velocity and acceleration are increasing. So we choose displacement. In the second figure, we see that the velocity curve is quite plain, while the displacement is decreasing and acceleration is increasing. So we choose the velocity. While in the third figure, we choose acceleration, since acceleration gives us a plane curve as compared to velocity and displacement. Then we have the, as I told you earlier, that we have this important component in our chain, that is the detector or averager. Now the vibration level that we obtain by using sensors is the one shown in the left diagram. First, it has a low amplitude, and then its amplitude increases suddenly, and then it's become like the previous one, it's low again. So by using an averager, we convert this single frequency curve, this vibration time curve, into three different curves. Now there might be noise, there might be our required sound, and all of this has been changed. It has been converted into three different signals. Then we have different peak-to-peak hold value, peak-to-peak, and peak and RMS value as compared to the first one. So this averager is very important component. Then we have averaging time with the help of an averager. In the vibration and time system, the vibration level might be unsteady, and then we use the averager to steady it and smoothen the curve. The average time is 1 second, and then it is 10 seconds. By increasing the time of the averager, we get a smoother, planar curve. Now we see signal versus system analysis. First we have the signal analysis, and then we have the system analysis. In the signal analysis, we attach the sensor on top, and it senses the vibrating signals, while in the system analysis we attach the vibrator, and then we use AMOLED for the excitation purposes. In these two figures, we see two different analyses, and we discuss them further in the coming slides. Now to conclude what we have discussed, and to move on to the further part, to the next part of our video, let's see that from this lecture we learn how to choose the right vibration parameters, We present the measured data in a suitable way, we understand the basic filter and analysis parameters and limitations, and we understand the difference between signal and system analysis. Now we have vibration transducers and signal conditioning. Let's move on. First of all, we have the same measurement chain that we have been discussing from our first video. This is an important chain, and the processes are very useful to us to obtain our required output. The early methods of vibration measurements were, let's say, back-aged, outdated for now, because back then we used to touch the machine to measure its vibration, and we could use a stethoscope or we could use a rod and put a rod on the vibrating machine to detect the vibrations, to measure them. But now we just use sensors. Okay, and other was to use a mechanical lever on a shaft, and this lever would oscillate, giving us the vibration levels. It is not much used nowadays, it is outdated. Now we have vibration transducers, mechanical levers, and measures displacement. We have the advantages that it is self-generating, the trace is available, and it's inexpensive. The limitations are there is no electrical output, we have low frequency, and we need high amplitude vibrations to measure. We cannot measure the low frequency, or we cannot measure the low amplitudes, and it wears out pretty fast, loses the vibrating structure because we have to put it in contact with the structure, and it's sensitive to orientation. Nowadays we have eddy current proximity probes that measure the change in resistance while not even being in contact with our required machinery. Its applications involve relative motion, shaft eccentricity, oil film thickness, etc. Now, eddy current proximity probe, it measures displacement mostly according to API 670. Its dynamic range is given, frequency range is given, and we have its advantages that it's non-contacting, no moving parts, there is no wear, and it's worked to direct current. Second, we have velocity pickup. Now, the sensor is attached on top of the motor as shown on the above figure. Now we get E is equal to B over V. We have the limited frequency range and we measure its vibrations. We have its limitations that moving parts are prone to wear. It has a large size, it is sensitive to orientation, sensitive to magnetic fields, high lower limiting frequency as it operates above resonance, friction against the motion of the moving element will cause reduced output signals. And finally, we have the piezoelectric accelerometer. Now this is the most important one, and this is most widely used since it gives us the maximum number of applications that give us our desired output. The piezoelectric accelerometer is attached on top of the machinery, and we get the following results as are shown in the next figures. Now, its dynamic range it's given, its limitations are that it's high impedance output and no true DC response. Now, its advantages that are very important to us are that it's self-generating, there are no moving parts, so there is no wear. It is rugged, it is very large, it has a very large dynamic range. It has a wide frequency range, it is compact, it has low weight, so it impacts low weight on the machinery. It is highly stable and it can be mounted with any orientation. Then we have the piezoelectric materials, that when a force is applied to a piezoelectric material in the direction of its polarization, an electric charges develop between its surfaces, giving rise to a potential difference on the output terminals. The charge and the voltage is proportional to the force applied. The same phenomenon will occur if the force is applied to the material in the shear mode. Now we have 6 different types of accelerometers. There's planar shear, there's center-mounted compression, there's theta shear, there's annular shear, there's delta shear, and then we have ortho shear. We have P denotes piezoelectric elements, R denotes clamping ring, E denotes built-in electronics, S denotes spring, B is base, and M is seismic mass. Now, compression type design and shear type design. What is the difference between these two types of design? In the compression type design, this traditional simple construction gives a moderately high sensitivity to mass ratio. In the center mounted configuration shown, the piezoelectric element mass spring system is mounted by means of a cylindrical center post attached to the base of an accelerometer. The design is very stable, but even with careful design, the influence from environmental parameters is higher than for the other construction types. Therefore, this design is especially used for accelerometers which are intended for measurement of very high shock levels and special purpose accelerometers. Next, we have shear type designs. In the shear type accelerometers, they have the advantage that they intrinsically are rather insensitive to environmental parameters like temperature transients and base strain. A high sensitivity to mass ratio can be obtained, and this helps to create miniature accelerometers as well as high performance general purpose accelerometers. The piezoelectric elements are arranged in such a way that they are subjected to shear forces from the seismic mass when accelerated. Now we have the operational range of vibration transducers. We see eddy current proximity probes, we see velocity transducers, and the piezoelectric accelerometer. First of all, we discussed the usable ones. These 3 are currently being used as the modern detectors. The eddy current proximity probes, they have a shorter amplitude range while they have a large frequency range. While in the velocity transducers, it has a limited frequency range and similarly a limited amplitude range, while in the piezoelectric accelerometer, we see that it gives us a great range of relative amplitude and frequency. That's why it is the best one to use for our required purposes. How do we choose an accelerometer? General purpose, medium weight, and sensitivity, or small, light, and high frequency? What are the parameters that we have to keep in mind to choose an accelerometer? Here we see that the weight is different from 10 to 50 grams, while the fluctuations are, the sensitivity ranges from 1 to 10. While in the blue region we see that its sensitivity ranges from 0.1 to 0.3, so it has very low sensitivity, but the weight is lower as well. So we have to consider that it has to be of lower weight, so when we attach it to our required component, it doesn't impact in its motion, it doesn't hinder its motion. Now we move on to the useful frequency ranges. There's first we give input and then we get the required output. We see the 10% rise. This is our required value. First we have a base of, it is gradually, first we have a constant line, then it gradually increases, gives us a peak, and then it goes down. Now here we have the accelerometer that gives us in meter per second square, in meter per second square, and then we have frequency, and then we can see the frequency range. Here we have 35 decibels. Then we have sensitivity and frequency ranges. The sensitivity and frequency are, the sensitivity is given on the y-axis while the frequency is given on the x-axis in kilohertz. We see that the smaller detector has a low sensitivity, but it goes to high frequency. Now this will be expensive, and the middle one has a higher sensitivity and a greater but a lesser frequency as compared to the first one. but the biggest one has the greatest sensitivity and the least frequency range. So this would be the most applicable one to use in our requirements. This is mostly used in machinery, in factories. We have sensitivity and frequency ranges as explained in this paragraph. Then we have accelerometer mounting, which is fixed. We have three different mountings. There is thin double adhesive tape, there is cementing stud, and then there's stud mounting. Now, beeswax or the thin double adhesive tape gives us a smaller peak and then it goes down, while the cemented stud gives us a bigger peak, and the stud mounting gives us the highest peak on the decibel level. So this shows that the stud mounting would be the most applicable one, the most usable for our requirements. Now we have accelerometer mounting handheld. We have three different types. There's handheld probe, there's inverted probe, and then there's a magnet. We see three different curves. The handheld probe, it gives us a peak before the rest of them at a lower frequency. The inverted probe gives it at a greater frequency, but the magnet gives it at the greatest frequency. So in case of handheld accelerometer mounting, the magnet is the most reliable one. We have mounting with the aid of a permanent magnet. It is an easy and fast method of mounting the accelerometer is by using a permanent magnet, which very easily can be shifted from one position to another. This is especially useful for surveying. The method is restricted to use on ferromagnetic surfaces, and the dynamic range is limited due to the limited force of the magnet. To obtain the maximum frequency range and the dynamic range, the ferromagnetic surface must be clean and flat. By fitting self-adhesive disc on the magnet, it will provide electrical isolation between the accelerometer and the surface to which it is attached. Now we have the isolating the accelerometer. How do we isolate it? There is electrical method, and then we have the mechanical filter. In the electrical method, we have the prevention of ground loops, and for the mechanical filters we have protection against high shocks. Both these isolating the accelerometer diagrams are given, and it can be understood from the concepts that we have gained from the previous figures. Choosing a mounting position. Now, at which position do we mount our sensors? Now, at the A position, it is closer to our vibrating body. It isn't causing any disturbance to the mass, so we can put it at the A position. But if we put it at the B position, it is way too far from our vibrating body. It will not note the proper vibrations, so we do not use the B portion. Now at the C portion, it is away from the line of action and closer to the vibration, so C is applicable, but D comes straight in front of the vibrating body, so it will hinder its motion. It might even cause a resonance. It will give us more problems than our required solution. So the reasonable positions for mounting will be A and C. Now we have loading the test object. We have three different test objects, and we see how they can be loaded. The dynamic mass should be less than 1/10 m, 1/10 of the mass. Now this is a law that we have to follow. And we have these different ranges that we have to keep in mind. We have the transverse sensitivity. We don't go into depth with this slide, but if you can understand it, it's good, but if you don't worry about it. Then we have triboelectric noise. How do we overcome it? We can use a flat tape to cover the wire to give us a constant piezoelectric effect and to overcome the triboelectric noise. Then we have environmental effects such as base strain, humidity, acoustic noise, corrosive substances, magnetic fields, and nuclear radiations. We have calibration, high temperature, triaxial, and then we have shock. We use high sensitivity with built-in amplifiers. And this is the calibration chart is shown. We have to keep certain parameters in mind while selecting our required detector. Then we have force transducers, where we hit it with a force and we transduce a force and then we observe the vibrations. Accelerometer check using mounted resonance technique. We have a mounted resonance technique which is utilized as an accelerometer check. The points are given as explained. We have calibration using back-to-back method. In this method, the calibration is using one end is connected at one end is connected at one side and the other end is connected at the other side. Then we have preamplifiers for piezoelectric accelerometers. We have the choice of preamplifiers. Which one do we choose? Do we choose the voltage preamplifiers or do we choose the charge preamplifiers? Then we move on. Single-ended or floating input. We have either single-ended input or we have floating input, and how do we use it in our chain. Now we conclude our lecture that this should provide you with sufficient information to select and use the right transducers for your measurements, select and use preamplifiers for your transducers, set up a working measurement chain, and avoid general problems like good loops. That's the end. This concludes my second video, and thank you very much for watching. Please leave your feedback in the comments below.